To navigate physical space with agility, an object requires command over the geometry of its environment. In three-dimensional space, that command requires specific control over how a body translates and rotates. This wireframe diagram demonstrates the baseline spatial reality. There are three axes of spatial translation: moving forward and backward along the x-axis, left and right along the y-axis, and up and down along the z-axis. There are also three axes of rotation. The drone can tilt up and down, known as pitch. It can tilt side to side, known as roll, and it can spin on its center point, known as yaw. These 6 movements combined constitute the 6 degrees of freedom required for spatial control in a three-dimensional environment. A standard quadcopter chassis possesses a specific mechanical limitation. The machine possesses exactly 4 scalar inputs, the rotational speed, or RPM, of its 4 fixed motors. This is an underactuated system. The physical degrees of freedom outnumber the available control inputs. There are 6 ways the drone needs to move, but only 4 throttles to manage those movements. To understand how 4 motors command 6 degrees of motion, we must isolate the aerodynamics of a single spinning propeller. Quadcopters achieve stable flight through continuous, high-frequency asymmetrical force cancellation. We can begin by isolating the variables of a single motor and propeller. A propeller's primary function is to generate vertical lift by displacing air downward. As shown in this diagram, that generated lift is directly proportional to the square of the propeller's angular velocity. Cutting through the atmosphere creates resistance. As the blades spin, aerodynamic drag acts against their leading edges. According to Newton's third law, every action has an equal and opposite reaction. The energy required to push the blades through that air resistance results in a force applied to the motor stator. This is reactive torque. If the propeller spins clockwise, a proportional twisting force is applied to the motor in the exact opposite direction. The upward lift generated by the propeller is tied to this proportional twisting force. A single rotor system with no structural countermeasures cannot maintain a fixed heading. Without a way to counter the reactive torque, the motor base will spin in place, driven by its own angular momentum. Because mechanical propulsion creates rotational instability, the system must achieve net zero torque to maintain a stable position. The standard 4-rotor cross configuration addresses this rotational instability. In this layout, the diagonal motors are paired. Motors 1 and 3 spin clockwise, while motors 2 and 4 spin counterclockwise. This arrangement ensures the competing reactive forces cancel each other out across the chassis. When net torque equals 0 and total upward thrust equals the weight of the drone, the machine achieves a stable hover. Horizontal movement is possible even without a dedicated forward-facing thruster. This is achieved through differential thrust. This demonstrates a pitch maneuver. To move forward, the drone decreases front rotor RPM while increasing rear rotor RPM. The rear generates more lift, shifting the center of thrust and tilting the chassis forward. As it tilts, vertical force redirects horizontally, providing forward acceleration. Rolling left or right follows the same logic, utilizing the left and right rotor pairs instead of the front and back. During these maneuvers, the total RPM across all 4 motors remains mathematically constant. The drone moves laterally without losing altitude because the net upward force is maintained. Horizontal movement is the result of unbalancing the spatial distribution of thrust while maintaining total net lift. Pitch and roll solve X and Y translation. The final degree of freedom is yaw, the ability to rotate on the z-axis without tilting or losing altitude. Yaw operates independently of thrust vectoring. In a stable hover, the twisting forces from the clockwise and counterclockwise motors are balanced at 0. To yaw right, the drone increases the RPM on the counterclockwise diagonal pair and decreases the RPM on the clockwise pair. This maneuver requires 2 of the motors to slow down. Because the RPM reduction on one diagonal pair is matched by the RPM increase on the other, the sum of vertical lift remains constant, and the drone holds its altitude. However, the reactive torque is now unbalanced. The counterclockwise motors generate more rotational friction than the clockwise motors. To conserve total angular momentum, the chassis absorbs that excess twisting force and rotates in the direction of the weaker motors. During this rotation, the drone remains level, as no vertical lift is vectored horizontally. Yaw utilizes aerodynamic drag, the friction of the air against the blades, to pivot the machine. In flight, a drone rarely executes these maneuvers in isolation. It manages pitch, roll, and yaw simultaneously while adjusting for variable environmental conditions. Managing these variables requires a flight controller. When an operator provides a command, that input must be translated into 4 specific motor speeds. This linear mixing matrix serves as the mathematical bridge between pilot commands and the RPM values for the 4 motors. It calculates compound maneuvers by summing the required RPM differentials for each axis, computing the resulting net value. This computational loop occurs thousands of times every second, adjusting motor speeds based on gyroscopic sensor data. This processing occurs automatically, correcting for the machine's inherent mechanical instability without pilot intervention. While the hardware consists of 4 fixed motors on a frame, flight is the product of high-frequency mathematical adjustments within the control matrix.